Let us first review some of the concepts we learned in physical modeling. First, let's look at a simple electric circuit. Here we have a battery. Remember, battery is represented by long, short line. The long represent positive, and the short represent negative. Here is the path, and we draw a resistor. Incidentally, there are two different ways to draw a resistor in a circuit. The common method for this one is usually found in US and Australia. You may also see people draw the resistor like this, and this will be usually found in the UK and the European. So both methods, they are correct. We want to look at the simple electric circuit from the point of view of energy flow. If I say where is the energy supply, is from the battery. And incidentally, battery is a way to convert chemical energy to electrical energy. And through a process called electrochemistry process. So the energy starts from here. This is how energy flow. And when energy flow along the path, we assume there's no energy lost in the path. But this is just a assumption. So if you think about a power station, very often the power station is far away from the city. And there's a huge energy loss when they transfer the electrical energy from the power station to where the energy consumed in the city. But within the circuit, we can always assume there's no power or no energy lost. Next, so where is energy dissipate? In this simple circuit, the energy dissipate in the resistor. The word here called dissipate is mean lost, but it has a very specific meaning. It means once the energy is lost, you cannot return back to electrical energy. Most likely, it will lose into thermal energy. Or more commonly, people say heat energy. But I want to address here, technically, we should say thermal energy instead of heat energy. Because heat energy technically is not correct. Heat is a process, it's not an energy. So the energy related to the heat transfer is called thermal energy. So resistor is the one to dissipate, or where the electrical energy convert. So it is a way, if you look at from this point of view, it is electrical energy transfer into thermal energy. And this transfer is one direction. So we use the term dissipate. Another thing about resistor, we always use the term called load. When people say, what is the load of the circuit? We always mean it is the resistor. Number 3, in this case, what physical quantity describes how fast energy is transferred? How fast, it means related to time. So energy transfers how far. So you are talking about delta energy, how much energy transfer within 1 second. So it's energy per unit time. Now we know the unit for energy is joule and time is second. So this physical quantity, we give it called power. So power is the physical quantity, describes how fast energy is transferred. And we give a common name. We call this one watt, or the symbol is W. Let's look at what's the meaning of voltage. If current can be think of like a water flow, so voltage can be thought of a pressure difference. In a water pipe, if water flow because there's a pressure difference. So in the electric circuit, if there's a voltage difference, so we have a current flow. Now let's look at it from another perspective. I usually think a battery is like a factory, and in the factory there's a train coming out. This train passing through the railway and return back. When the train coming out from the battery, the train carry coals. So this is like our energy. So we now ask, what carry the energy? It's the carriers. So in our analogy, it's the train, and you can think of like a charge. They carry the energy. Now this train move around and until it reach here. This is called their energy, and then it will deliver this one to the house and burn it. So the energy carried by the train or by the charge will convert. After passing through this one, the train remain unchanged. You still have train, so you still have charge. But the energy of the charge already transferred to another form. So this become thermal energy, and this is where the resistor. So this train will passing through here, and here the energy will be refused, and this is our battery. So what is voltage? Voltage is the electric potential energy. How much? Carried by each unit of charge. So we call this electric potential. Now remember, electric potential is electric potential energy per charge. So if you look at here, and you can find this one, this is 1 volt, mean 1 joule of electric potential energy per each coulomb of charge. What is the physical meaning of voltage? So I will say voltage tells us how much energy each coulomb carries. Power is the rate of energy transfer. So 1 watt of power means 1 joule per second. So watt, it just means joule per second. Energy versus power. Energy describes the total amount of energy used. Energy also is the unit for describe the work done by force. Remember, in physical modeling, if you have a force push an object for a distance d, we will say the force does positive work and it is equal to force times distance, and the unit is joule. So work done also described by the same unit as energy. It means joule. How about power? Power is described, of course, the rate at which energy is transferred. Now, you will find commonly in the electricity bill, you will be billed as kW hour. And let's break it down. Kilojoule hour. So kilo is the prefix, so it's 10 to the power 3, and it means this is 10 to the power 3 joule per second. And then you ask, in each hour, how many seconds? It is 60 times 60 seconds. And you can see now the second cancelled. And this will become times 10 to the power 3 joule, or 3.6 times 10 to the power 6 joule, or 3.6 megajoule. So if the electrical company say you use 1 kilowatt hour electricity, it means you use 3.6 megajoule of energy. That's why they charge you this based on the kilowatt hour. Let's look at some simple calculation. You have a battery here, and this is a resistor. The battery is 12 volt and the resistor is 6 ohm. 2. Use Ohm's law to calculate the current. The current starts from the positive side of the battery, passes through the resistor, and use Ohm's law, V equal to IR. So I equal to V over R. So you got 12 volt over 6 ohm, and it is 2 ampere. 3. Calculate the power dissipated in the resistor. You can calculate the power by 2 different approaches. First, we can say P equal to VI. So the voltage across the resistor is 12 volt in this case. 12 times 2. And this is 24 watt. Alternatively, you can calculate P using I square R, and the I is 2. So 2 square times 6. Again, you got 24 watt. Both methods are correct. Number 4. explain the power means physically. So the power means in each second 24 joule of electrical energy convert into thermal energy. If you put heat, it's acceptable, but again, thermal is better. Here is a simple electric circuit. This is the voltage V, and this is R, and this is I. Now, if you want to measure the current through the resistor, you must disconnect the wire and insert the current meter. And we put A here in between. So what I say is the ammeter or the current meter is connected in series. So when you have a voltmeter, you want to measure the potential difference between 2 points. So you connect your voltmeter in parallel to the resistor. So for the voltmeter, you want to connect it in parallel. Because first, ammeter, it measures current, measures current at a point. Therefore, you want to break the circuit and connect in series to voltmeter. Voltmeter measures the potential difference. Remember, say the difference. So it means between 2 points. Therefore, it is connected in parallel. Let's look at a real-life example. Here we have an electric kettle. It says it weighs 2,400 watts. This number is also called the power rating of the electrical appliance. And the voltage is 240 volts. Now it says, what does 2,400 watt mean physically? So it just means the kettle converts 2,400 joules of electrical energy every second. If the kettle operates for 3 minutes, 1. Calculate the energy used in joule. 2. Energy used in kilowatt hour. So number 1, energy used equal to power times T. Remember, power is defined as energy per second. Therefore, how much total energy used during the period of time is power multiplied the time. and the power is 2400 times 3 minutes, 3 times 60, so it is 432,000 joule. Number 2, kilowatt hour. So E is equal to, this one is the number expressed in kilowatt multiply the number or the time expressed in hour. So our power expressed in kilowatt is 2.4. So 2.4 is enough. And you can say kilowatt times 3 minutes, it means 3/16 hour. So remember, this is a unit. Now if you multiply these two numbers, you will get 0.12 kilowatt hour. Now these two numbers must be the same because it just expresses the energy used in a different unit. First is expressed in joule, and the second is kilowatt hour. Remember previously we discussed 1 kilowatt hour is equal to 3.6 times 10 to the power 6 joule. So you can always convert back or multiply this number and multiply this number, and you should be able to get 432,000 joule. In terms of the cost, because the electric company charge you 30 cents per kilowatt hour, so all you need to do is 30 cents 0.3 dollar per kilowatt hour. And how much energy you use? You use 0.12 kilowatt hour. So you can say this and this, they cancel, and you got a number, and this number is equal to 0.036 dollar. Why do electric companies charge for energy rather than power? Because energy is really how much you use, and power is just energy per time. If you use a electrical appliance for a long time, it means you use more energy and therefore you should pay more. So charging for energy makes sense. And also traditionally most company will use kilowatt hour, because most of the electrical appliance, their power rating is stay in kilowatt. So it just say if the power rating is stayed in kilowatt, just like the case in kettle, and then you ask how long you use this electrical appliance in terms of hour. Say I use it for a certain hour. All you need to do is multiply these two and get a number. And this number here, the new number, you know this is the unit of energy, a new unit. It corresponding to this one. And the electric company can just multiply this one for the rate. I mean, each kilowatt hour, how much they are going to charge you. In this example, it is 30 cents. Let's look at some practice problems. Problem number 1. A 50-volt battery is connected to a 5-ohm resistor. So A, we can just use Ohm's law, V equal to IR. And I equal to V over R. And 15 volt over 5 ohm, of course, is equal to 3 ampere. B, the power dissipated. P, you can use VI. It means 50 volt times 3 ampere. So you have 45 watts. Problem number 2. We have two resistors, 4 ohm and 6 ohm. They are connected in series, and the power source is 20 volts. First, we want to find the total resistance. Because the two resistors, they are connected in series, so we are saying is this circuit is equivalent to this simple circuit, and we call this RS, the equivalent circuit for two resistors connected in series. And RS is just the sum of the two resistors. They are connected in series, so it's a 10 ohm. Now the current here, I, so we ask what is the current passing through this simple circuit, and this current I is equal to 20 volt V over R, and the R is the equivalent resistance or the total resistance. This is 10 ohm. So the current is 2 ampere. Now if we look at back to the original circuit, it means the current is start from here, also 2 amp, 2 amp, 2 amp, here also 2 amp, here also 2 amp. The current in a series circuit remains unchanged. So we can now apply Ohm's law on the 4 ohm resistor. And same, we apply Ohm's law on the 6 ohm resistor and find the potential difference across each resistor. For the 4 ohm resistor, V, this is the potential difference across this resistor, and this is equal to IR. I is 2 amp, R is 4 ohm. So you have 8 volt. For the 6 ohm resistor, V equal to IR. I remains unchanged, the same, 2 ampere, but this time the resistance is 6 ohm, so it's 12 volt. Now note, when we add the two voltages, and it's equal to 20 volt, so this is the overall voltage. Number 3. If a lamp stay, it is 100 watt. So this is again we call the power rating of this electrical appliance, and it runs for 2 hours. So this is of course the time. So what is the use in joule? So in this case, you have to say energy equal to power multiplied time, and the power is 100 watt, or clearly joule per second, same, times 2 hours. Now remember, you must specify the unit in second. So this is 2, each hour has 60 minutes, each minute 60 seconds. So this is the time in seconds. So the answer is 72,000,000 joule. Puppy, energy in kilowatt hour. So first we have to express our power here in kilowatt. 100 watt, it means 0.1 kilowatt. And now we express the time in hour, 2 hours. So the energy E, if this time we don't use joule, we use kilowatt hour. So we can just say 0.1 kilowatt times 2 hours. Remember, this combined is a unit of energy. So this is 0.2 kilowatt hour. Just remind you again, this is another like a big unit. This is 3.6 times 10 to the power 6 joule.